La 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 la. All right. I'll begin with a word of prayer. Okay, I'll just start. Dearly Father, we thank you for this day, and I thank you for these students. Just ask you to be glorified in what we do. We'd all understand a little bit more about linear algebra today, Lord. In your name I pray, Lord Jesus. Amen. All right, so today I'm talking to you guys about dual space. Although I suppose what might be helpful to us before I get into the dual space is just to mention a nice isomorphism that I probably should have thrown in, before. If we define, let's say, psi, a mapping from, linear transformations on, let's say, from Fn to Fm to m by n matrices, it's nice to notice that we have an isomorphism here. The isomorphism is simply given by the following. So like psi of, say, the linear transformation t is equal to what? The standard matrix of t, right. And that is exactly the isomorphism. Because you can check it's clearly onto, it's one-to-one, it's linear, it's everything. So it is a linear bijection. And among other things, this proves that the dimension, right? What's the dimension of the set of all linear maps from Fn to Fm? Well, it's equal to the dimension of this, right? Which, by the way, is m times n, right? How do I know that? Well, we can look at the matrix unit basis, right? So the matrix units, the EIJs. Sounds kind of like a Wookiee. Takes a certain amount of violence to get that out. I should probably task the violent one to that. But let's see here. Anyway, so isomorphism. So let's go on. Dual space. So definition, given vector space V over a field F, we define the dual space, V dual, equal to simply the linear transformations from V to the field. All right, that's the dual space. Now, so if your vector space is finite dimensional, right? What can we say? If the dimension of V is equal to n, then the dimension of V dual is the dimension of the set of linear transformations from V to F, right? But I wasn't greedy enough over here. You could also make an isomorphism, right? Let's say psi beta gamma, a mapping from the linear transformations from V to W to Fm by n. Supposing, of course, that the cardinality of beta is n, the cardinality of gamma is m, and those are respectively bases for V and W. And then my isomorphism for a linear transformation on these abstract vector spaces, well, guess what? It's the matrix of the linear transformation. And again, you can prove that that's a linear bijection. It is explicitly actually formed by the composition of invertible maps. So, yeah. If you don't like this, you could also like build it on a basis and extend it linearly. Anyway, it is an isomorphism. And so with that isomorphism in play, what's the dimension of the linear transformations from V to F? So like, you see what I have here? The dimension of the linear transformations from V to W is actually equal to what? It's equal to the dimension of V times the dimension of W. Again, all of this is supposing that V and W are finite dimensional, but that's the deal. So what's the dimension of the linear maps from V to F? Yeah, so the vector space W is F. What's the dimension of the field with respect to itself?
Would that just be the dimension of V?
How many dimensions, if you take the real numbers, as a real vector space, what's the dimension of the real numbers?
1.
1, right. So F is a one-dimensional vector space over F. So I mean, applying what I just wrote over there, this is the dimension of V times the dimension of F. When we're talking about F dimension, so that's just the dimension of V, because the dimension of F is 1. And what does this mean then? The dimension of the dual space is equal to the dimension of the space, so what can we say about them?
They're isomorphic.
Thus, yep. V is isomorphic to its dual. So there are some things in this course which are, they work well in finite dimensions, and they work the same in infinite dimensions pretty much. This is not one of those. Okay, so like the dual space of an infinite dimensional vector space, it's bigger, usually. I think it's always bigger. Like the algebraic dual to a vector space, it could be much bigger than the vector space in some sense. And so when you study infinite dimensional vector spaces in a course called functional analysis, what you'll do is you don't look at the full dual space. You'll look at the dual space, you look at the elements of the dual space which satisfy another condition. You look at the so-called bounded linear functionals. Or equivalently, you'll assume continuity of the dual vectors that you're interested in. In other words, you don't look at the full algebraic dual space. You look at some kind of restriction in the study of functional analysis. So I'm just saying that if you think about the dual space in the infinite dimensional context, there's like lots to learn there. Okay, but it's not this course. It's another course, probably grad school. All right. But in finite dimensions, it's simple as this. All right, and we're going to mostly be talking about finite dimensions today. So yay. What happens if you take the dual of the dual? What is V double dual? It is literally the dual space of V dualed. What would that mean? We'd be talking about linear transformations from where? From V dual to the field. All right? And in the context of finite dimensions, right, this is going to again be isomorphic to V. So if the dimension of V is less than infinity, then V is isomorphic to V dual, and by the same token, it's isomorphic to V double dual, right? Because what is V dual but a vector space, right? And we just proved that any vector space is isomorphic to its dual, so we just apply the theorem again to the dual space. All right. Now you might wonder, what are examples of dual vectors, right? And by the way, a vector in the dual space is called a dual vector. I know, not a very imaginative name, but there it is. And so here's another definition for us. For x in a vector space V, let eval x, not evil, but eval x be a mapping from V dual to the field, defined by eval x on alpha is equal to alpha of x for all alpha in V dual. So you guys, so it's the evaluation map, all right? Is this a linear transformation? Like, let's just, it's not in my notes, but like, let's just take a second and let's prove that this is the linear transformation, right? So how would we do that? Let alpha and beta be elements of V dual. And well, let C be a scalar, a number in my field. And we'll pick x to be a particular vector, okay? If we calculate eval x of C alpha plus beta, by definition, that's what? That's C alpha plus beta evaluated at x. We just plug it in, right? But what's the definition of that evaluation? Like, how do we evaluate a linear, like how do we add linear transformations? Pointwise, right? So like the definition here is that that is equal to C alpha of x plus beta of x, right? This goes back to what is our definition of how we add functions, right? We add functions pointwise. Remember, linear transformations are just a particular subspace of function space, so it falls under that. And then what? This is what? This is C times eval x of alpha plus eval x of beta. This shows that eval x is in fact a linear transformation of dual vectors. Okay? Thus, eval x is an element of the things that it takes in dual vectors, right? And the output is scalars. In other words, eval x is an element of V double dual. So this evaluation map is interesting because it actually, it shows us how we can build an isomorphism from a vector space to its double dual. Here's how you do it. So we can define a mapping psi from a vector space to its double dual. And how is it going to go? Basically, we just do psi of x equal to eval x. Some other things I write, sometimes you'll just like, you'll see people sometimes put like an x hat over this or something. Like it's the double dual vector that corresponds to x. And how does it act? How does x hat act on a dual vector? It's simply by evaluation of the vector. Yep.
You said it's from V to V double dual.
Oh yeah, I said that, but I didn't write it, did I? Yeah, sorry about that. I'm getting too stingy in my my markings. But yes, it should be the double dual for sure. Yeah.
So is it correct to say x hat is a transformation?
Yeah, x hat is a transformation of dual vectors. This is a way of taking a vector, which I think of vectors sort of generically as passive objects, right? Like I don't think about a vector acting on something, but this double dual isomorphism allows us to trade for a vector as a passive object for a vector as an active object, in the sense that the vector is a transformation, it acts on things. Dual vectors dual vectors are mappings of vectors, right? So in some sense, using the double dual puts the vectors on the same footing as dual vectors. This is used in physics a lot, actually. And also more generally like manifold theory. In manifold theory, typically the viewpoint is used that a vector is a derivation. A derivation is like an operator. So it's thinking of vectors as sort of active objects is done a lot in applied linear algebra, like at least for curved space calculus and stuff like that. But all right, back to here. So great, we have this, and what's interesting about this isomorphism, and you can prove that eval x is a linear bijection between v and double dual, and v and its double dual. What's interesting about this particular isomorphism is it has no reference whatsoever to a basis. You see, this is like evaluation has nothing to do with the choice of basis at all, right? So that's kind of neat. I will not chase the rabbit that just came into my head. Let's go on here. So next obvious question, anytime you talk about a new vector space, you're interested in what's its basis, right? So here's how that goes. And we're decidedly in finite dimensions here, okay guys? So let beta, and there's some kind of funky notation that just happens in this section, and I won't use it probably elsewhere, but you should see it at least, and so you'll see it here. This is a basis for v over f, okay? For each I in 1, 2, n, define v upper I, a mapping from v to f by linearly extending the formula vi acting on vj equals to Kronecker delta ij for all j equals 1 to n. So this Kronecker delta, I think I've told you guys about this before, but I'll remind you, it's 1 if I is equal to j, it's 0 if I is not equal to j, okay? So in this context, we say beta dual, v upper 1, v upper 2, v upper n is the dual basis to beta. And it's, I guess you could say for v dual, right? Now that begs a question, right? Which is, I've called it the basis for the dual space. Is it actually the basis for the dual space? And how can we prove that, you know? So it's in our best interest to write a theorem that, you know, lays out plainly the properties of the dual basis. All right? So let's do that. So notice that the upper indices is a notation, all right? They're not powers. It's just we're using a superscript for a label, all right? There's no danger here because we never square these things. So like, you know, I guess kicking the camera is better than shaking it violently. Let's see here. Where was I? Okay, so here's the proposition, 3.4.6. And it says if beta dual is as I just said, dual to beta, right, for V, then point number one, if x is equal to the sum I equals 1 to n of x upper I, vi, v lower I, then e upper I of x is equal to x upper I. Point number one. Point number two, beta dual is linearly independent subset of B dual. Point number three is that the span of the dual basis is the dual space. And if alpha is equal to the sum I equals 1 to n of alpha I v upper I, then alpha acting on v lower I is equal to alpha sub I for each alpha in V dual. All right. There's a little bit more I can say here, sort of, what's the word? Maybe to give you a better sense of what are these things, you know, because you always have that feeling as a math student when you run across a professor making some crazy new definition and taking you out of your comfort zone, right? And you're like, what on earth is the point of all this, right? What does this have to do with what we've already done? And I will get back to that. It does have something to do with what we've already done. All right, so let's see here. Let's work on part one. Okay? So the proof here, all right, so we've got let x equal to the sum I equals 1 to n of x upper I, v lower I. Then what happens if we calculate e upper j acting on x? What do we get? We have e upper j acting on the sum I equals 1 to n of xi vi. But how did we define the dual basis? We said extend linearly, right? We know that there's a unique linear extension off the basis. I've prescribed the values for the dual basis on the basis. Therefore, I have uniquely defined the dual basis on all of the vector space by that linear extension theorem. As such, it's linear. As such, I can pull out the summation, right? And I can pull out the constants, x sub I, and I'm left with e upper j. Aw, man. Dudes. Seriously? Not cool. Well, I see something escape my editing process. What is that e upper I supposed to be? What's that? V? Yes. That is supposed to be a v upper I. Indeedly doodly. So put a v here and a v there and a v everywhere. Woo! Just here, really. So we've got v upper j acting on v lower I. What would e upper I be for us? That would be the dual basis to the standard basis. So I don't want to do that, all right? Because we use e lower I to mean the standard basis in here, right? That's kind of like a set notation. I try not to contradict that, you know, as much as I can. Are you guys with me? We're almost done with this part. Is there any step that's unclear? All of it? Okay, well that's not, I don't really know how to respond to that. So we're working on the proof of 1, right? Our definition is that the dual vector acts on the vector to give us the Kronecker delta. So now we've got the dual vector acting on the vector. This is Kronecker delta, ij. The Kronecker delta is the natural enemy of the finite sum. It crushes it. Although it leaves one person alive to go tell the tale of its destruction. Right? It's like a witness to the mayhem. And the witness is I equals to j. So I is summed over, j is fixed but arbitrary here. J survives, and we just get x upper j. Because that sum is 0 for every I, except I equals j. That's what we claimed in part 1. See that? What's the significance of this, by the way? At this point, I can come back to that comment I made. What's the coordinate vector of x with respect to the beta basis here, guys? It's what? It's x1, x2, x upper n in my current notation, right? Which is what? So it's like v1 of x, v2 of x, vn of x. In other words, of course, this is also phi beta of x, right? And so one way you could look at what we're doing is we've discovered that phi beta has, in fact, component functions of the dual basis. The dual basis is nothing more than the component functions of the coordinate map. If you have a mapping into vectors, you can divide it into its component functions. These component functions are, in fact, the dual basis. So, anyway, that's part 1. Now that we have this, how will we prove linear independence? So I should be back to kind of your happy place more so, right? How do you prove linear independence of something? What do you do? We do what? Suppose sum I equals 1 to n of like ci vi is equal to 0, right? I'd like to show the coefficients are 0. What should I do? This is an operator. What should I feed it? Yeah, let's feed it v lower j. So if we let this, act on v lower j, we get the sum I equals 1 to n of ci v upper I of v lower j, right? But that, again, is the Kronecker delta ij. And once more, we've crushed the finite sum and left ourselves with just c sub j. But j is arbitrary. J is arbitrary. So we've just showed that this is equal to 0, for all j. Therefore, the dual is linearly independent. Yeah? How about spanning? How can we prove spanning? All right, so let alpha be an element of the dual space. Then alpha of x is equal to alpha of the sum I equals 1 to n of x sub I, v sub I, right? So I'm just using the fact that beta is a basis. all right? But then that's equal to the sum I equals 1 to n of alpha of vi, and I'm writing the x sub I over here, x upper I over here. So, all right, fine, fair enough. Like, can we agree that we can scale or multiply on the left or on the right in here? Like, I'm not going to take points off your proofs if you accidentally write scalar multiplication on the right rather than the left. I mean, if you reverse the order of matrix multiplication, I'm going to find you where you live and take away your stuff. But, you know, I'm sorry. I seem to be somewhat violent in my analogies today. But at least I didn't swear in here. It's good. So, as far as I know. So, what is that? Well, that's the sum over I equals 1 to n of alpha. I accidentally swore in differential equations this morning. It was not great. Anyway, I'm not getting into it. So this, by part 1, is vi of x, right? And so I'm just going to go ahead and write it like that. Part 1, we have that vi acting on x is x upper I. But then by the definition of how we add maps, I can pull the sum out like that. What does it mean if this holds for all x? See what we have? We have alpha of x. Aw, man, seriously? Nah. Right? Notice that that and that are equal for all x, so get rid of the x because it's a function, right? Two functions are equal if they are equal on all inputs, all x inputs. Therefore, we have just proved this. See, notice that the alpha sub I is exactly this. That's the coefficient alpha of vi. So put this all together, the dual basis is a basis. Yay! All right. And its significance, in part, is that they're the component functions of the coordinate map. All right. Let me go on here. So what are some examples of linear functionals? Do you guys know? There's one I've had you prove, guys. I've had you prove stuff about, right? You remember? What thing have we done in here where we put in a matrix and we get out a number, right? And it's a linear transformation. What is that? So, how about this? Trace is an element of the dual space of the n by n matrices. Right? Think about it. The trace of A is an element of F, right? Trace is in fact a linear map from matrices to numbers. It is a dual vector. Just to circle back to the, this dual basis business I was just talking about, you know what the trace of A is equal to? It's equal to what? It's, in my current notation, I probably should say it's A11 plus A, oh man, well, I may regret this. I may not be able to be consistent with my notation in this section if I'm probably walking right into something here. Anyway, you guys, it's fine. Let's just continue on. So you could look at that as E11 plus E22 plus da 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 plus ENN acting on A, right? Where I'm suggesting the notation that E upper ij acting on E lower KL is Kronecker delta IK Kronecker delta JL. So like if we work with a double index, that's how that looks. Right? When we work with matrices, we use a double indexing rather than a single index just because it keeps track of where things came from, you know. But conceptually, I and J as a package is playing the role that I did over there, you know. But anyway, that's the dual basis for like matrices. And here's how to write the trace as a linear combination of the dual basis. That's not in the notes. I just wrote it down. So another example is we could talk about V as like functions over the reals, right? And we could say alpha of f is equal to f of x naught, right? You know, let x naught be an element of R, right? I think this is really just what again? What is this alpha really?
Eval x.
It's eval x naught, right? So I mean, but the context is different here, right? Because f is just a continuous function. Is that linear? It's still linear for the same reasons we went over earlier. Because addition of functions is defined pointwise, and so because R is a vector space, we still get that that's a linear functional. So that's the one. Yeah. So, oh. Well, I'm talking about function space here, but maybe this would be let me just say this. If I swap this out for just a thought I had in passing, let me just throw it out there and you guys can take it for what it's worth. But if I let V be continuous functions on the reals, right? If we believe the rumor that my brother said, which is that you can prove that that has dimension of the continuum. Oh, never mind, those also. I will stop chasing this rabbit. Nothing interesting happened. I thought I had something there. I don't. Great. That's another example. Example 3. We could let V be an Rn vector. Define alpha of x equals to x dot v. Or if you prefer, you could write it as like V transpose times x. For this reason, sometimes people say that the dual vector to a vector is a row vector, because there's a natural correspondence between the dot product and row vector multiplications. So sometimes people will call dual vectors row vectors if they have this particular application in mind, but to me a dual vector is a more abstract thing. But nevertheless, alpha is a fact linear on x. And any choice of V, you get a corresponding alpha. So maybe a better notation here might be like alpha sub V. But anyway, example 4. If we have V as the continuous functions on the closed interval from 0 to 1, then we can have alpha of f equal to the definite integral from 0 to 1 of x times f of x dx. All right. Can you guys see that that defines a linear functional? No? Is it a number? If I take x times f, does this integral exist? Search your heart. It is true. Calculus 1, the integral of a continuous function is existing, right? Fundamental thermocalculus. So this integral exists. Multiplying by x still gives us continuous. And if I replace this with like CF plus G, well, guess what? Properties of the integral. That holds for all f and g. Therefore, alpha is a linear map on the continuous functions of the unit interval. So this is a linear functional. Definite integrals define linear functionals. How many of these can you build? You notice that I put an x here. If you think about this example, though, I could just as well have pretty much put any continuous function on 0 to 1 here, and this would still have defined a linear functional. What's the significance of these? Well, that depends on your application, right? This might be like, have a meaning in terms of like being a weight function from like an application in statistics or something, things like this. So there's lots to say there. All right, so next up, and you have a homework problem on this one, so you guys will hopefully appreciate this because I'm kind of working part of your homework. I say homework, I meant quiz. By the way, I do have a solution to that quiz, and you're welcome to look at it if you want. I mean, I have a solution to a good part of it, and you're welcome to look at my solution if you can find me. I don't think I have it with. I don't know if I have it with me. Let me get to the point here. Definition. If, although Daniel says one of the solutions is wrong. So, well, I don't know. We've been down this path before, haven't we? But I think he's right. I think I miscopied the problem, so he's got a point. Define the annihilator. The annihilator of W in V dual by ANN of W equal to alpha in V dual, such that what? Such that alpha of x is equal to 0 for all x in W. In other words, the annihilator is the set of linear functionals on the vector space which kill everything in the subspace. They kill everything.
Or violence, metaphor.
There's lots of violence, yes. The annihilator method is also upcoming in differential equations. So it's very exciting. Yeah, it's not this one, though. But yes. So that's a definition. Now, theorem. If W is a subspace of V, then the annihilator of W is in fact a subspace of V dual. So, I mean, technically that's kind of part of one of your homework problems, but so it would be good for you to write this up in the homework problem where I ask you something about annihilator subspaces. Like this is like the first thing I would prove in that homework problem. Okay? So, yeah. So let's see here. If 0 of x is equal to 0 for all x in V, then 0 is an element of V dual, right? I mean, that's the 0 dual vector. It just maps everything to 0, okay? The 0 transformation. Is that in the annihilator? Nope. That 0 times, x is equal to 0 for all x in W. Thus, 0 is an element of the annihilator of W, which apparently is not equal to the empty set, right? How do I know that the annihilator is a subset of V dual? it's built into the definition, right? It is by assumption a subset of V dual. So we have a subset of V dual, which is non-empty. Now what does it take to prove that the annihilator is a subspace? What do I do? Let what? Yeah? No? Okay. How about C is a number, and I usually use alpha and beta for dual vectors. It's just, you know, I don't know how I was raised, I guess. So let alpha and beta be in the annihilator of W. I'd like to show that the annihilator W is closed under linear combinations, right? Because then the subspace test will say it's a subspace of the dual space. So if X is an element of the of W, then check it out. C alpha plus beta acting on X is what? C alpha of X plus beta of X by the definition of function addition. But what do we know about alpha of X and beta of X? What are those? They're 0, right? By definition of the annihilator, these are 0. So C times 0 plus 0, which is equal to 0. Thus, C alpha plus beta is an element of the annihilator of W. And then by the subspace test, we have shown that the annihilator of W is a subspace of V dual. Okay? Yay. So one of your problems asks you to show that W1 is a subspace of W2, I think, is a subspace of V is given, I think, if I remember right in the problem. And you're asked to show the seemingly contradictory that the annihilator of W2 is a subspace of the annihilator of W1 is, wait a minute, did I get that right?
Yes.
That's what it says on the problem.
I think V dual, yeah. So what I've done for you today is to show you that these are in fact subspaces of V dual. And I think logically then all we really need to do is show that this is a subset of that to establish the claim in the problem. Because we already know that this is closed under addition by this. All right? So that's one thought I had for your homework. Another thought I had, something I haven't said but I should say, is it's easy to prove, and you need to use this in your homework in various places. Like if we have W is a subspace of V, that implies that the dimension of W is less than or equal to, I don't know if I ever wrote this in class, but I definitely should have because it's kind of like important. The proof of that simply rests on the basis extension theorem. If I take a basis for W, I can extend it to a basis for V, right? Either it works as a basis for V already, in which case the dimensions are equal, or I have to adjoin new things to it, in which case the dimension of V is strictly larger, if we're in the finite dimensional context, right? So I'm just thinking finite dimensionally here, guys, okay? So that's one thing. The other thing is the dimension theorem in the textbook is what I call the rank nullity theorem, if you hadn't noticed that already. The other thing is I have a mapping, a homework problem where I like quiz problem where I have like T, I think I was supposed to say L. It's fairly obvious, I think. Don't forget, I said you don't have to do problem 9, right? So the one thing that's left in this section, and I think there is a problem in your quiz about it, is the so-called transpose of a map. So if I have a minute, I'll show you. I don't have a minute, so I'll just talk about it. You can define, if you have a linear transformation from V to W, you can define the transpose of that map from W dual to V dual. There's a way to extend the map to dual vectors. And the cool thing is, if you look at it and you sort through how it works, the matrix of the transpose map with respect to the natural dual bases is, guess what? The transpose of the matrix with respect to the basis to start with. In this part of the notes, I use some up-down notation for matrices. And this notation is used in the book. You know, he doesn't have beta, comma, gamma. He's got like lower beta, upper gamma, or vice versa, I forget. So the book uses a slightly different like matrix notation than I do for the matrix with respect to a basis. So just, you should, you know, I'm sure you were aware of this. There's some other things in the book, right? If you haven't noticed already, the book uses this, right? But for me, that either means this or this if I'm working with polynomials in X or if I'm working with polynomials in T. My notation indicates the variable of the polynomial explicitly. You might say these are polynomial functions. You don't have to say the variable, they're functions, right? But anyway, this is part of a longer conversation that should be had in Math 422 about the distinction between an expression versus a function. But anyway, I think that's it for today, guys. So Friday, I will try to go over the solution to the quiz with you guys, and we'll get ready for the test is Monday, right? So can you guys prove linear independence? Right? You got linear independence, you got spanning, subspace test. These are the things the test is made of, right? Will there be a little bit of dual vectors or annihilators? Probably. Is it the full thing? No, obviously not, right? And you should be happy I didn't get to the transpose, so I can't test on that, right?